Hey everybody, welcome to Geology of Nebraska Week 9, and for today we're talking about the upper Paleozoic rocks, or the rocks that we can see at the surface in parts of Nebraska. So again, as we've been doing, let's just take a quick look at the geologic timescale to review where we're at. So we are now at the end of the Paleozoic era. So here, if you can see my cursor, the Paleozoic is right here. We are still in the Phanerozoic eon, and we are now in the upper portion of the Paleozoic, which includes the Pennsylvanian and the Permian rocks that are found at the surface of Nebraska, but they're also found in portions of the subsurface of Nebraska. So let's begin by talking a little bit about what the Pennsylvanian surface would have been like. The environments that were deposited in the Mississippian were mainly carbonate rocks. And if you remember back to previous virtual field trips and other lessons, carbonate rocks dissolve when they interact with water, which produces a karst landscape. Here you can see a diagram of the karst landscape on the left, which shows caves forming. As those caves form, there are collapsed features known as sinkholes. And we can also have these features called disappearing streams, which go into those sinkholes and run as groundwater systems. On the right is just a stock image of a karst landscape. You can see the carbonate rocks dissolving away by the pocketed surface that is there. The blue color of the water is also a product of carbonate weathering into the water. So basically, in the Pennsylvanian, we have this carbonate surface with collapsed features. And we can see this throughout the lower Paleozoic rocks and in upper Paleozoic rocks, but I wanted to mention it here. So this is an example from the Buffalo River area in Arkansas. The red line is highlighting an unconformable surface, and then there's actually a dip here in the rocks where they change. And this is a collapse feature where the younger rocks have collapsed down into the older rocks. This is an example of what's known as paleokarst, where we can see these karst features produced from the carbonate landscape in the ancient rock sequences. So now let's take a look specifically at the Pennsylvanian rocks at the surface in Nebraska. So we have seen these before, and this photo should look familiar. This is an image of Schramm Park. At this point in time, you should have started to recognize this sequence of rocks that we're seeing. The thick, ledgy rocks are limestones, and the sloped, softer rocks that look more weathered are shales. So what's different from the lower Paleozoic rocks is that the upper Paleozoic rocks have a much higher component of shale, and they also have some more terrestrial features in certain areas as well. So we'll take a look at that in a moment. So because these rocks have more shales, what exactly has changed and where are these shales coming from? So as a reminder, shales are a type of siliciclastic sedimentary rock. So remember, siliciclastic sedimentary rocks are made up of many mineral grains. Shales in this case are made up of mineral grains of very, very small clay-sized grains. But you need some sort of source for that weathered material to come from, and that source has to be from land. What exactly could have been sourcing the Pennsylvanian shales? Well, there are two possible options actually at this time. So, in the upper Pennsylvanian rocks, we start to get the early Appalachian and the Ouachita Mountains forming from this orogeny or this mountain building event happening to our east. That would have uplifted mountain ranges, very, very fresh mountain ranges. So in your lesson today, you'll see that at this point in time, they were growing similar to how the Himalayas or the Andes mountains are growing today. So they would have been shedding a lot of sediment to their west and to their east. There's also evidence of what are known as the Paleo Rockies or the Colorado Mountains at this point in time as well, to our west. So we could have been receiving sediment from both of these sources. So what exactly is the evidence for the Paleo Rockies? It's almost been completely erased. So the Paleo Rockies are very different from the Rocky Mountains that we see today. That was a separate orogenic event that happened during the Mesozoic. But what we see is that there's actually siliciclastic sediments or reddish shales that had to have formed from some sort of sediment source. And the only layers that we see left of this orogenic event are actually in Colorado, and they're rather famous. So if you've ever gone to a concert at Red Rocks concert venue, then you've been literally rocking with the Paleo Rockies, because that is the last 300 million year old evidence of a mountain range that has been almost completely eroded away. So we see that in the Pennsylvanian and Permian rocks, there's this sequence of cyclic sedimentation. And this cyclic sedimentation is at a much quicker frequency than what we saw in the lower Paleozoic, which is something distinct. So these layers are changing at a faster rate. And it's indicating also rising and falling sea level, but under different environmental conditions, and as I said, on a faster time scale. So on the right here is an image of one of these typical cyclothems. It still starts with a basal sandstone, but these are predominantly non-marine sediments. So we're seeing a shallowing sequence where we have sandstone, sandy shale to fine siltstone, freshwater limestone, and then coal. Then this is overlain by predominantly marine deposits. Very deep marine shales and shallow limestones alternate through this sequence with many marine limestone fossils. So what does this indicate? Changing sea level yet again. But what exactly was changing sea level at this time? Well, if you look in Gondwana and near the South Pole at the time, you will also find evidence of glacial striations and other glacial features. This indicates that there was a southern polar ice cap at the time, which we can see in this paleogeographic reconstruction at the South Pole, right? So there it is. And the red box is highlighting where Nebraska is. Now, we already know that glaciers and ice sheets store a lot of water as ice on land. So when that water is released, it rises sea level or raises sea level. And when that water is stored, it lowers sea level. So here, this is a very great explanation for what was happening during the Upper Paleozoic. Now into the Permian, we're still seeing this kind of rising and falling sea level sequence, but there are some distinct differences. We see an increase in the number of red beds and terrestrial sediments that form as Pangea is finally coming to completion. The color red in rocks comes from being oxygenated, which typically happens above sea level, so it's indicating a drying climate. Again, here's another image of a paleogeographic reconstruction. This one would be in the Permian, and this is to highlight that yes, we have that southern polar ice cap, but at this point in time, we have another supercontinent that has formed, and this is the very famous continent of Pangea. Now, what you'll notice is that most of the land surface is near the equator, and then we've got it going further south and north, and that there's not very much seaways, so our shallow interior seaways are gone, and there's these dry patches of land. Now, life on land was very interesting at this time, so there are labyrinthodonts, so there's a lot of different amphibians that are moving onto land. So labyrinthodonts and temnospondyls are types of amphibians that got very diverse at this time. On the top, this Limnoscellidae reconstruction is one of those labyrinthodonts. And then down here, we have a temnospondyl fossil. And then there's also early reptiles that are thriving at this time. So for the remainder of this week and even into next week, there's a really nice episodes of PBS Eons, if you've ever heard of that. You can find them on YouTube, so I encourage you to explore those videos yourself if you're interested in fossils and ancient life, and many other geologic topics, actually. But I've created a page this week of PBS Eons videos that are relevant to any of the topics that we're discussing today. So I encourage you to take a look at those just to stave off your own curiosity, if anything. More life on land. So in the Permian, we start getting these mammal-like reptiles. So most people do not like the term mammal-like reptiles anymore. But there are some similarities to both there. So typically they're referred to as synapsids. Now, synapsid refers to how many holes you have in your actual skull. So there's a diagram here in the bottom right showing different skull features. On the left is the skull of an anapsid. So we have our orbit or our eye socket, but no other holes behind that or fenestrae. We can have a synapsid skull, which is what we as mammals have. This has one temporal fenestrae behind the orbit or the eye socket. And then there are diapsids, which have the orbit and then two temporal fenestrae, and that's what reptiles and dinosaurs have. Now these, at the time in the Permian, were synapsids, so they have a skull shape very similar to modern mammals, more similar to modern mammals than to reptiles. But they diversified during the Permian, and so here are some images of these. Again, take a look at those PBS Eons videos for more information. Now we end the Paleozoic and the Upper Paleozoic with a very, very large extinction event, the largest extinction event ever in Earth history. And so here we're just going to briefly talk about what could have caused that. This was a major extinction event both in marine and terrestrial environments. So instead of just looking for an explanation that kills ocean animals like some extinctions or some that just kills terrestrial animals like others, you have to look for something that really reconciles this large-scale extinction. So there are a few possibilities. There could have been quite a bit of volcanic darkness and cooling from volcanic emissions, which could have released sulfur dioxide and other toxic noxious gases into the air. This could have influenced acid rain development, which all would have factored into plant death and food chain collapse, major soil collapse and soil erosion. And then that major soil erosion would have put an influx of nutrients into our oceans, causing lots of algal blooms. When there are major algal blooms, they die and sink to the ocean floor, and bacteria reduce that down and use up oxygen, creating really low oxygen environments. And those low oxygen environments kill off the organisms that are living in there. And then at the same time, you're also getting ocean acidification from that acid rain. So really it all factors into these greenhouse gases again and these emissions from different things. And there's lots of different hypotheses still on how this actually functioned. But this is just a synopsis of the system that could have contributed to that mass extinction event. All right, so for today, that is all we're going to discuss for our mini lecture. And I hope you enjoy the rest of this lesson.